Okay, sorry to interrupt everyone's anticipated coffee break, but we have some breaking news, a discovery made within the past month. I'm Marcin Glowacki. I'm giving this talk from the UK on behalf of the Craft Survey Science team. There's a lot of people listed at the bottom who have been involved with this discovery and follow-up. I'd like to stress this was a team effort. A lot of other people here could easily give this presentation. However, a lot of the team are in Australia, which is a pretty unfortunate time zone for this conference, so it falls upon me. I also just like to pay acknowledgement to the native title holders and traditional owners of the land on which ASCAP works from, Iriyaramana Ilgara Bundura. And this is some artwork which depicts the craft survey as distant objects that burst and flicker. So that's a nice description of FRBs, if you like. So the FRB in question is 250613. You heard on Monday from Yuan Ming about the craft survey as well as the craft coherent or crackle system. But while that was in operation, we actually made this detection for the old system, the incoherent sum system, or ICS for short. And this was sufficient to get a detection. This was found during the EMU survey. So as a reminder, craft is a commensal survey. Whatever ASCAP happens to be observing, be it spectral line, polarization, or radio continuum, this was the latter. We just piggyback and stare for FRBs. This was during our observation less than 20 minutes long. We had the trigger just late on the 6th, also late on the 13th of June by UTC time. And this was during ASCAP low observation, so centered at 920 megahertz and almost 300 megahertz bandwidth. The reported DM was just shy of 175 DM units, and the signal to noise was not super high, but 12 was a firm detection. Another thing I should note, one of our PIs, Ryan Shannon, was overseas. We've actually noticed a trend where he or Keith Bannister or both will be away mysteriously and then we'll suddenly detect a fast radio burst. So this is something that needs further investigation. But on a more serious note, since we're using the ICS system, we didn't have the initial position. We could identify which beam from the 36 beams of ASCAP that it was brightest in, and so we have a beam center position, but this meant that we had to do some offline processing to determine the localization, because at the time it was a one-off burst for us. So we used Celebi, which is a pipeline that we use to process on voltages. ASCAP is constantly recording now 12 seconds worth of voltages, and when we have a trigger for an FRB, we dump those voltages, move them to a supercomputer in Melbourne, and then we can process those voltages to get the localization, as well as get high time resolution data set. Celebi is also a Pokemon, but it's also called the Craft Effortless Localization and Enhanced Burst Inspection System. This was initially started by Danica Scott, a PhD student I've co-supervised. A list of several names here of people who have been involved in the continued development of Celebi. And I've bolded the names of Tyson, Aperba, and Adam because they use Celebi in this particular case to process the voltage data. So after we did some match filtering to determine in what time and frequencies the FRB was most visible in, we get this image of the FRB itself. And from there, we can determine its position, which is given on the bottom left. And the error means that we have a sub-arc second precision on this localization. And happily, this aligns very nicely with this optical image. So the background image is the legacy or Decal's DR10 R band, and the ellipse is the FRB localization ellipse. This source is a 22 mag host galaxy. So if we stick it through path, which is what Alexa Gordon did, we have a probability greater than 90% that this is where the FRB came from. This source does not have a spectroscopic redshift. It has a photometric redshift of about 0.2. So if you assume that redshift is the real redshift, then this would apply when you combine with the magnitude, a low mass galaxy. But we are currently looking into optical follow-up and analysis is in progress, so we can determine a firm redshift measurement for this FRB and hence its host. And as I mentioned earlier, Celebi also produces a high time resolution dataset. It can actually go down to 3 nanoseconds in resolution, which is very rarely needed, but quite useful if you happen to detect a dead satellite that goes off after 50 years in operation. But in this case here, we saw two pulses as part of this one-off burst, and it had the stereotypical sad trombone structure here, which made us quite excited. And then from the Celebi data products, we then also discovered that the rotation measure was a whopping more than 7,000 radians per meter squared. You can also notice this is directly from the second component. Around where the cursor is, there is an RM forest also appearing at around that peak. Dyson Dyer has also done some further investigation after doing some Faraday derotation. This is what the two pulses look like at this time resolution. The top panel is PA, middle panel is Stokes I, L, and V, and then you have the Stokes I dynamic spectrum at the bottom. And you can see from the first component that it lacks polarization. There's not even a strong linear polarization, which is unlike the second component, where it's much stronger there. We also did some quick checks. We were able to fit some scattering to the second component. We're still working with the first one, which is a little bit more complicated. We get about 57 microseconds of scattering timescale. And when we look at the power law index, it comes to -4. So roughly what you would expect a well-behaved FRB to be like. And we also looked at scintillation from both components. We get a modulation index of roughly 0.7. So these were the numbers that we had from our initial burst. We had strong evidence that this was quite some exciting thing to follow up. Firstly, we looked at the existing observations from the EMU survey with ASCAP. We didn't see any radio continuum, but ASCAP is a fantastic survey instrument, but not the deepest one, so this didn't rule anything out by any means. We were keen to get more time, but firstly, as a reminder, Craft is commensal with ASCAP survey. So whatever ASCAP is doing, unless we happen to have our own time and can request it, we're stuck with what it's doing, and they decided it's time for some maintenance. So we couldn't use ASCAP anymore, and in fact, it was a bad time to be a radio astronomer in Australia because even the likes of Parkes was also having maintenance for several weeks. Luckily, we're able to make a request to the Meerkat operators for some follow-up, and they allocated us some time for a DDT. So we were given two sets of observations. One of them was a 2-hour observation, and another one was a 6-hour block, which was split into 2 times 3 hours by the Swayo system. These were both daytime observations, and we did notice some RFI between the two. Data analysis is currently ongoing for what we have transferred over. And while we didn't see anything in the first observation, and RFI didn't help, in the second observation we saw this repeat here. This was the first one that confirmed that this FRB is a repeater, thanks to Misha Caleb, as well as Ben Stappers and the Meertrap team in general for this. You can see the parts that have been blanked out due to RFI, but we see a clear, well, 22 signal-to-noise detection of a single pulse. And that wasn't the only one. In fact, we found 16 bursts within that second observation. This is a particularly bright case, more than 100 signal-to-noise. And again, 2 pulses showing up here with the stereotypical sad trombone feature. Now, since Meerkat is deeper, we were firstly able to eye the surreal data-reduced images for each individual track. And even there, we were seeing hints of radio continuum. So myself and Andy Wang have combined the data sets and then reprocessed them. He used Oxcat, and I did a sanity check with the process Meerkat pipeline where we got similar results. So this is the image that Andy produced, which gives you a peak flux of 24.2 microjanskis. Now, this isn't necessarily PRS. It could be, but since we only have so good angular resolution of our observation, this could also be attributed to star formation within the host galaxy. So we will need higher resolution follow-up, but this is encouraging that there is a chance there is actually some PRS associated with the host galaxy of this FRB. In the meantime, while we're investigating optical follow-up, question was, can we also use that Meerkat data to look for H1? This was a 4K resolution spectral line, so not particularly high resolution, but it will be sufficient. And this is something we have done before for an ASCAP FRB. Shameless plug here, where we had a FRB that was detected behind the galactic plane, so it was a bit harder to get immediate optical follow-up. but we were able to detect the H1 emission line, which then gives you a redshift, and that was later confirmed by the optical to be the redshift of the host galaxy.
Okay,
Unfortunately,
2 minutes left.
Perfect. Unfortunately, there was no emission to be seen. I certainly wouldn't bet on any of these peaks to be corresponding to the host galaxy. This was a daytime observation, which is not ideal for spectral line astronomy, but I can say there's several actually H1-rich galaxies within the field that have popped up quite obviously from looking at the dataset, but nothing toward the host. So here is a plot showing on the y-axis log MH1 mass, and on the x-axis the redshift. So you can get a limit on how much gas would be in a galaxy depending on where redshift is, up to 0.09. Unfortunately, there's a lot of RFI, as you've seen on the earlier plot, just south of 1300 megahertz, which really hampers your ability to find anything of H1 higher than that. So while there could actually be a decent amount of gas in this galaxy, it might be just too high redshift for this H1 approach to work. So we're really going to have to wait for the optical, find out further. I also highlight that a few days ago there was a separate ATEL following ours, where a team using GMRT have also seen repeats from this FRB, and they've found repeats all the way down to 300 megahertz. So we encourage further follow-up where possible of this FRB, and we're also exploring options as well. So I'll leave you with the summary slide. We've successfully detected a repeating FRB. It has one of the largest rotation measure magnitudes so far, and there is some tantalizing radio continuum emission aligned to the position and seemingly a small host galaxy, but we do need that redshift to confirm. Thanks again to Meerkat and also later GMRT follow-up to confirm this is a repeating FRB. Thank you very much.
All right, thanks a lot. Are there any questions? We have time for maybe one or two. Any questions online? Well, then I guess, I'll pass to Ziggy.
Hi, this is Ziggy Pleunis at the University of Amsterdam. It seems like the Southern Hemisphere hasn't really been probed very well for repeating sources, so there might just be very hyperactive sources waiting out there to be discovered. Do you have any clues on how we could find them?
Short of more observations, not really. Maybe you could try targeting nearby clusters or the like. That maybe will be something that would lead to a repeater, more dense environments. But otherwise than that, we just need more observations.
Hi, Marcin. This is Calvin from UC Berkeley. Great talk. I noticed that unlike the other FRB systems in dwarf galaxies, this one has a relatively low total DM. So I'm wondering if you can break down the DM budget a bit more for us. What's the ISM and Halo contributions in that direction?
I think the Milky Way contribution is, from memory, roughly 40 DM units. And so it could be, if you assume that given the high RM, that it might be a significant host DM contribution as well, which would place it roughly, from the rough approximation less than redshift of 0.1. But yeah, we need to investigate this further. And analysis of all the repeat bursts, which maybe will help us give us some more clues on that, is underway.
Great,
as
thank
well
you.
as optical follow-up.
Of course. Oh, is that a direct?
Hi, I'm Kavya Shaji from University of Sydney. So I was just curious, since the bursts detected were bright, were they were removed from the visibilities while doing the imaging?
I don't think we did any removal from the voltage data. We just localized what time they were happening and then imaged it directly from the voltage downloads. I'm not familiar with the data sets from Meerkat, how that has been processed.
Okay, sure, thank you.
This wouldn't have been bright enough to see with a raw Meerkat image that we were looking at ourselves, at least to my knowledge.
All right, I think that's it for time. Let's thank the speaker again. Yeah, and before the end of the day, where we're going to, those of you who want, going to do the lab tour of Matt Dobbs's lab, we're going to have one special announcement about next year's FRB 2026. It was Google Slides, yeah.
Yeah. The FRB 26, yeah, in China.
I did. I'm blind right now.
Bottom.
Yeah.
Yeah.
Yes.
This one. Yeah.
Yes. Oh, and I'll share it for the people online.
Okay, so I'm Wang from University of CES. On behalf of the whole SOC and LOC, I'm honored to be here to announce that the FRB 2026 will be held in Guiyang in China. So actually in China we have so many selections like Beijing and Shanghai. They are big cities, big and modern cities. So, but we finally decided to hold the meeting conference at in Guiyang because we think that the Beijing and Shanghai, even they are famous cities, but they are so boring because they're just big large cities with modern buildings. So. We select Guiyang because Guiyang are surrounded by by green mountains and rivers and limestones. So the Guiyang is a typical coastal landscapes, which was caused by some dissolution of the soluble rocks. So you may find that there are so many beautiful places like river, like lake, like the lakes are with green and blue colors, and also so many beautiful caves. And there are also some ancient Chinese buildings in Guiyang. So it's a very beautiful city. I think people don't worry about the security because China is very safe. And also don't worry about the visa because the China allows the people, the ordinary passports to retire for visa-free tourism within 10 days for some countries. So and very major highlights to announce in the conference is we have a chance to visit the FAST telescope site. So as you know that the FAST is the largest single dish telescope in the world. Due to the great sensitivity, the FAST is a very powerful instrument to monitoring FRBs. So we will have a chance to visit the real platform of the FAST site. So whatever you are tall member or short member, you will be roughly this size here. Yeah. So under you will go to the platform here, and the FAST site is under your feet, and then you can see the whole site. That is so impressive. So bienvenue en Guiyang, bienvenue en Chine. Welcome to China, welcome to Guiyang. So thanks, we really hope you're coming.
Thanks. So yeah, I think that wraps it up for the talks for today. For the guided tours, Matt, are you going to be taking people over to Rutherford or? We'll divide into 3 groups. Yeah, and then the conference dinner is at 6:30 at the Thompson House. So thanks everyone. Wait, is that right? Thompson, okay.
Tech changes while we wait for his presentation.
All right. Well, thank you very much for the opportunity to speak here today at a late-breaking session. I'll be presenting a result from CHIME on the radio brightest flash of all time, which is CHIME speak for the highest signal-to-noise ratio FRB that we've ever detected. So before I kick off, this work was kind of collaboration work in the truest sense of the word. We were drawing on expertise from all corners of the kind of CHIME collaboration. And all this work was kind of synthesized together heroically by Amanda, who led the effort to turn this into a great science paper. Thanks for that. Great. And so this burst, which we've kind of affectionately titled RB Float for the Canadian affinity for root beer, especially for some people at the top. Amanda and Jason, I'm looking at you. And so this burst is interesting because it's extraordinarily bright in the data. So that gives us a high precision. So the first kind of word that went out about this burst was in Natel by Mawson, where basically we had detected this largely very high fluence burst towards a galaxy that was only 40 megaparsecs away. So this puts the burst at an energy that is kind of not atypical for the FRB population, but because the burst is so close to us, it gives us a really high fluence. Now that in and of itself is not unheard of in the literature. Certainly there are publications of side lobe FRB detections in CHIME that have kind of similarly high fluences. But what makes this burst special and kind of different from those cases is that it was detected at near maximum sensitivity in the CHIME telescope. And so what we can see here is a function of CHIME's primary beam and synthesized beam sensitivity as a function of declination. And the white line kind of shows us here at 60 degrees that the burst was detected at near optimum kind of sensitivity. Then in the axis that's collapsed here for right ascension, we formed several synthesized beams across the sky in that direction. And this X marks the spot. So this burst was detected within the full width half maximum of one of those, putting it really at kind of the highest sensitivity that we can achieve. This means that our high fluence burst converts to a very high signal to noise ratio signal. And that's great for a lot of different science, including kind of outrigger localizations. So coincidentally, this burst also is the first localization with each of the outrigger instruments, which, as a reminder, kind of ascend in baseline length from CHIME to KKO, then HCO, and finally GBO on 3,300 kilometer baseline. So each of these CHIME outriggers is kind of like a 1/8, or in the case of KKO, I think even smaller, version of the array that lets us perform higher precision localizations. In this case, the high sensitivity or the high signal to noise ratio of this burst allows it to be localized to several tens of milliarc seconds, which at the very nearby host galaxy gives us a projected localization of 11 by 13 parsecs in actual distance. Now that's awesome because it allows us to really investigate the kind of the circumsource medium and say something about the progenitors that we might expect for a burst like this. So what do we find? So if we do dive into some of the spectral information that was retrieved from Keck, the Cosmic Web Imager, we see that in H alpha and in O2 that the burst kind of is on the outskirts of a high intensity line emission region. If we kind of take spectra on that star-forming clump and at the FRB localization, and then we kind of perform some line ratio testing, we can see that the spectral lines that we get there are consistent with being on this like star-forming path of the field galaxies that are kind of in the region. And so we think that this is an indication that basically the FRB is on the outskirts of a star formation region at a separation of about 190 parsecs in projected space. Similarly, the H alpha emission measure at this localization kind of gives us some estimation of the DM that the burst accrues as it passes through, or well, if it passes through this H alpha region. That kind of implies that it gets like 60 to 110 parsecs of its DM, which is only 160 total. Which implies itself that the burst is kind of at a depth of between 10 and 50 parsecs through this region, if indeed it is background to that clump. Similarly, there was JWST follow-up of this localization. And so we kind of coordinated an effort, which was mostly led by Wenfei, to kind of cooperate with these people and publish a companion paper with Peter Blanchard to make a great interpretation that combined this JWST data with the localization that we had. So they identify a couple of different near-infrared counterparts that are near to the localization, naming them NIR 1 through 5. And they kind of go into depth on what the NIR1 could be, which is this faint globule here within the 1 sigma localization region. They say basically it could be a red giant or a massive main sequence star that is at the location, and that could be in a binary with a compact object producing your FRB, and it could be, undergoing common envelope phase or Roche lobe overflow. And similarly, a dust echo could explain the emission at this region, so they're going to do follow-up later to see if a transient nature can be ruled out. The things that they rule out at this location include kind of young star clusters and globular clusters, pulsar wind nebula, and supernova remnants, and similarly an isolated magnetar. Some of these are not bright enough to explain the emission that is seen at this region. They do make a point of noting, though, that the young stellar population kind of in the general vicinity of the localization means that if it's not NIR1, there's a pretty good chance that this burst is associated with core collapse supernova from it's the remnant that comes from that process. So moving on from the localizations, we also can do great morphology study with a high signal to noise signal. And so we do some scintillation and a scattering analysis, measuring kind of a scintillation bandwidth of about 14 kilohertz and a scattering time of about 0.4 milliseconds. As we've seen in a few other talks this week, you can use this to form kind of 2 screen constraints on where you expect an extragalactic and galactic screen to be. If we do something similar and we estimate a galactic screen from NE 2001, this gives us some constraint on where the extragalactic screen can be, and it has to be within about 60 parsecs of the FRB location. If that FRB location is then backgrounds to this H alpha region, and that H alpha region is causing the scattering, it kind of means that our FRB has to be localized very close to that star-forming clump in 3 dimensions. Similarly, with polarization, we see some stuff for the first time in FRBs, including this known effect in pulsars. That's the flattening of the polarization position angle as you average out over scattering. Underlying that averaging, we see that it's kind of got a larger swing than most non-repeating FRBs. And similarly, the Galaxy RM is consistent with 0, although with a wide error bar, which makes it the lowest of any polarized non-repeater. So that's the things that we find, but what do we not find? Because that can be just as important. Well, in supernova studies of this galaxy kind of go back a long way, or at least the optical data to look for those transient events. And so we end up with pre-burst data about 20 years on this galaxy that shows that there's no kind of optical emission consistent with a supernova at that location, ruling that out for that period. And I believe this is the longest baseline of optical data pre an FRB. Which is exciting. Similarly, we don't see any compact persistent radio emission at this location at a number of different frequencies. So I think this is at 4.9 gigahertz with the HSA and then 9.9 gigahertz with the VLA, placing the kind of deepest limits on non-repeating source using radio follow-up that rules out a nebula 10 times brighter than the crowd. Similarly, we don't see any X-ray emission here, although there was kind of an initial reaction that there was an Einstein probe transient similar to that location. Subsequent Chandra data rules out that as being coincident with the outrigger. But we place kind of upper limits on the maximum X-rays that can be emitted from this location that puts a stopper in it being a bit of a ULX instead. And so that's inconsistent with one of the interpretations from the JWST data. Now to the meaty part of this is that we get good constraints on how repeater-like this FRB can be. So previous to the burst, we have about 265 hours of FRB data, kind of over 6 years of regular monitoring from CHIME. And there was a dedicated campaign following this up with Omar and others that gave us kind of hyperflash data amounting to 210 hours in these kind of different bands shortly after that burst. So as a reminder, the hyperflash is the high cadence kind of monitoring from these telescopes distributed across Europe. And by forming those, you get really sensitive limits on what repeater emission can come from a dedicated kind of line of sight. So if we put all of this together, we can trace out on this curve, kind of as a function of energy, the cumulative rate that we see, given that there are no repeat detections found in subsequent data. And this allows you to trace out basically an energy curve that looks like so. So our data on the right is the kind of actual data that we fit to this point. That was the burst that we observed at this energy. And because no bursts were detected at lower energies, your cumulative rate kind of flattens off quite substantially. Now then, your error bars are covered here in the 3 sigma region. Also plotted here are the observed repeat distributions in energy from other repeating sources. And what we find is that the shape of these increases so much in the number of bursts you see as a function of energy that there's just no way you can fit that distribution, regardless of its absolute rate scaling, into the allowed region for this 3 sigma statistic that we have here. And so this means that basically this is one of the tightest constraints on repeat, like saying something is definitively a non-repeater that we have so far, with some caveats about clustering, given that some of the hyperflash data is quite centered in time. But we're pretty convinced. And so this is analysis that you can do that is empowered specifically by having high sensitivity at that localization, given that it traces through the CHIME beam, and that the rate required of high energy events to have this detection within the small part of the CHIME beam that is very high sensitivity has to be large enough to push this cumulative rate out here to make it high. And so that gives us, that's a nice conclusion from the paper. And so with that, I'll kind of leave you with the key takeaways from this that are, for the first time, we have the CHIME outrigger localization with all 3 of the outriggers giving us a sub-arc second localization. And we also kind of propose that this burst is localized in 3 dimensions with scintillation and the scattering analysis that puts it within 10 to 100 parsecs of the H alpha region that it was found on the outskirts of. We find that it's kind of not consistent with being a repeater and seems to have a fairly clean radio environment with no PRS. And so with that, I'll be happy to take any questions from people. Thank you very much.
Great talk, Mawson. Oh yeah, I'm Lauren Rhodes from McGill. Thanks, Mason. I had a question about the say continuum follow-up. So in terms of both the radio and infrared, are there plans to continue monitoring, see if anything appears, like this infrared counterpart, are they going to keep observing, see if there's anything that changes?
Yeah, so I know that in the infrareds, they have particular plans to follow up later with JWST to investigate this idea that it could be a dust echo. So dust echo, for people that are unaware, is, you have a supernova or something go off or some kind of energetic event that releases a lot of radiation. And at later times, that radiation gets reprocessed by dust into infrared emission, but that can come at a delay to that event. And so that is like some expanding bubble of light that you would see reprocessed into your line of sight. And so you have to look later to see if it goes away because it's some kind of transient event. And so I believe, yeah, the JWST team plans to do that follow-up.
Thank you.
Any more questions?
Hey, Mawson, this is kind of a plant because I'm pictured on some of these slides. But how do you know? How do you constrain the low energy end of the repeater, the repetition rate distribution?
Yeah, so this is like part of the analysis that's kind of well empowered. So this line of sight transits through our beam. We're highly sensitive to that particular line of sight, and so we get good limits in that we don't find any other repeating bursts at lower energies. Given that this burst was, I think, in the integrated time detection system has a signal to noise ratio of thousands. And so we really could have found follow-up bursts down to a very low level. And so and fast could as well. Yes. Fast could as well, yeah. I don't know if there's been particular fast follow-up of this line of sight just yet. There has been. I'm seeing nods in the audience, so they also haven't found anything, I expect.
Okay, great. If there are no further questions, let's thank Mawson again. And our last late-breaking talk of the morning will be by Dotan on a periodicity search in one particular FRB.
Hello, thank you for letting me tell you about this periodicity search. So first let's get right into it. Yes. So I think we talked a bit throughout the week. Why should we search for periodicity? Just the very clear smoking gun if you consider a magnetar or some neutron star progenitor. Why I tell you about this particular source is that there's been a claimed detection of periodicity in this, and I was initially very excited and then turned to reproduce and kind of want to dispute that. So how do we actually search? So initially we should choose our data, do some cleaning, some pre-processing on it. Then we should define what our actual, what are we searching for? So setting the frequency range, in this case, like 0.1 Hertz to 10 Hertz. Then the frequency spacing is set by the data we consider. Choose the statistic, either something that will tell you whether the bursts that you have when you fold them on for the trial period, whether they line up or are they still scattered around. You can do it with some H statistics, some bind chi-squared. And for the significance estimation, I repeat the message by Daniela that you should, if you can, do Monte Carlo. So I'll focus mainly on 2 points that I think make the difference in my and Du et al.'s analysis. First, the pre-processing, the threshold on the waiting times. So for this particular source at this particular kind of time of observation, this is what the waiting time distribution looks like. And you can clearly see that there is like a long mode and the short mode, and it's dangerous to take the short mode into your analysis as well, while not taking it into account when you estimate the significance, because when you have those bursts that are very close by, when they travel in your folding, they will naturally just line up, and your statistic will be very much biased by it, and your significance estimation would turn out to be incorrect, to overestimate the significance. Basically, Monte Carlo is how you get those kind of plots and get this observation that you overestimate the significance. Yeah, so to wrap up, we have this source, and it doesn't seem, when you cut the short waiting times, it doesn't seem to have to show periodicity. So we need to be careful about what you take into your periodicity analysis. Thank you.
Any questions?
This is Casey Law from Caltech. I wonder if is there sort of a principled way, like a physically principled way of making that selection between the short and long? Or are we just arguing that they're physically different things? That's the point.
That depends on your interpretation, I guess. You could make either a test, whatever you like, but when you estimate the significance, either do it like consider the number of the ones from the short, because it just, if you sample only from the long distribution, you'll estimate your significance wrongly. So if you reject some of them, then sample from the distribution you actually use. Yes.
Sure.
And we'll take one online question before we move to the next person. Yes, you can go ahead and unmute and we'll have the next speaker come down.
Yeah, can you hear me?
He's online.
Hello.
Go ahead, sorry.
Yeah, it's Pranav from Bonn. Thanks for the nice talk. I had similar question on what Casey said is for a pulsar in waiting times, we will see a nice harmonic peak, a nice peak followed with harmonics. So did you also try to test how to sample the waiting time distribution burst, and if you change or decrease the sample of burst or give a varying cut in the waiting time, does that change the significance?
Can you repeat shortly? I didn't catch what do you want to do with the waiting time distribution?
No, so you're talking here about where to give the cut in the waiting time distribution to select the sample to do the periodicity search on. Is it have you also tried if it gets sensitive to how much you vary this cut and if you select different portions of the cut?
No, I did not. I just saw, I think in this case, it's very clear that you have two separate kind of components in the waiting time distribution. So again, either you choose one of them and sample from it, or now you need to say what are you doing, whether you keep the number of some number of samples from the short distribution or do something else. But anyway, you should do the periodicity search and the significance estimation on the distribution of TOAs that you sample from.
Okay,
Great.
thanks a lot.
Okay, let's thank our speaker again.
Hear me? Can you hear me, Mason? Haochen, if you can hear me, Amanda, can you nod?
Yes, I can.
That's sick.
Amanda.
Haochen, okay. Hello, testing.
Yeah, give us a minute, Haochen. We're almost gonna start. Yeah, sure. Feel free to go and start share your screen. Yeah. We'll get started like a minute or two. Can people see the slide? Yeah. Okay. Should I start now? Oh, no. The chair will introduce you. Okay.
Everybody go find your seat. We're going to get started. So our first speaker, or our first session of the day is going to be another two late breaking talks. And the first talk of the day is by Haochen Wang of MIT, who's going to talk about the detection of large-scale cosmic baryon distributions with FRB dispersion measures from CHIME FRB catalog 2. Take it away, Haochen.
Great. Yeah. So good morning, everyone. I'm Haochen Wang. I'm a graduate student at MIT. I'm very excited to tell you about this detection of large-scale cosmic baryons from CHIME FRB catalog 2. So first, why do we care about cosmic baryons? You probably have seen this already from Liam's talk yesterday. But again, I'm showing you the gas column densities from two simulations with identical initial conditions. The simulation on the left has stronger feedback, pushing baryons outside of galactic halos. And this results in a much puffier gas distribution. And feedback on the right is weak, so gas clusters more tightly with galaxies. We know that the diffuse hot IgM is extremely difficult to observe, and this makes baryon distributions arguably the biggest uncertainty in cosmic structure formation at 10 megaparsec scale or below. And this seriously limits the power of upcoming weak lensing surveys that require this information to do precision cosmology. But the good news is that the FRB DM counts all the electrons along the line of sight, and this gives us the ability to probe baryon distributions and galaxy feedback. So here, I'm showing you the dispersion measure from CHIME FRB catalog 2. The full catalog has around 4,500 FRBs, but for this analysis, we remove FRBs along the galactic plane, as shown here in galactic coordinates. So we remove those FRBs with galactic DM contribution larger than 100 DM units, because their contribution will be rather uncertain. So after this, there are about 2,800 FRBs left. We then remove the galactic DM contribution from all of these remaining FRBs. So now you are looking at a map that's extragalactic DM only. So given this map, we can apply a traditional power spectrum analysis technique, very similar to what people did to the CMB map, computing the CMB power spectrum that gives us the variance of scale, variance of cosmic structure as a function of scale. So in principle, we could do something similar and compute the DM power spectrum from this DM map. But the problem for us is that our sky is only sparsely sampled by point-like FRBs. So we can mitigate this by cross-correlating our DM measurement with another large-scale structure survey that has much better coverage. For example, galaxy number counts from a galaxy survey. So in this study, we use 6 million BGS galaxies from the DESI legacy survey with photometric redshift. So although we don't have redshift information on our FRBs, we can nonetheless extract the tomographic information on electrons by cross-correlating our DM with galaxies across different redshifts. So in this analysis, we group galaxies in 5 photometric redshift bins, from redshift 0.05 to 0.1, 0.1 to 0.2, and all the way to redshift 0.5. So the cross-correlation between our entire DM sample and with the 5 galaxy redshift bins gives us 5 DM galaxy cross-power spectra, each measured at a different galaxy redshift. So this quantity tells us the relative clustering strengths between the electrons and galaxy distributions as a function of angular scales on the sky, with small l corresponds to roughly tens of megaparsec, much, much larger than cluster scale, and high L corresponds to roughly hundreds of kiloparsec. So we are looking at smaller scales close to galactic halos. And the dashed horizontal line indicates 0 correlation. So overall, we can see that there is a correlation on the large scale, the supercluster scale. And as we go down to smaller scales, as we approach galactic halos, we see that the cross-correlation strengths decrease. So to really understand what's going on, we need a model for what we just measured. So in this little cartoon here, I have Milky Way on the right, and the galaxy shell represents one of the galaxy redshift bins. And all the star symbols represent FRBs in our catalog. So recall that the galaxies, they are all within redshift 0.5. So we expect many FRBs to be in the background of the galaxies, as indicated by the blue color here. Their signal goes through the foreground galaxies, picking out electrons around these galaxies, adding to their dispersion measure. So the cross-correlation between DM and the galaxies give us a term that's proportional to the electron galaxy power spectrum measured at the galaxy redshift. And other FRBs, they're located within the galaxy shell. So their positions will correlate with galaxy positions, giving us another cross-power spectrum that's measured between the FRB and galaxy locations. And finally, some FRBs are in the foreground. They do not correlate with background galaxies and do not contribute to the signal that we measure. So now I'm showing you the full expression of the signal model. This may look very complicated, but again, it is just a weighted sum of two power spectra. One due to background FRB DM correlating with foreground galaxies, and the other due to positions of FRBs correlating with galaxies within the same redshift shell. So this signal model requires 6 fitting parameters. Not all of these parameters are shown explicitly in the expression here, but 4 of these parameters describe the FRB population. The power law index alpha describes FRB number density as a power law. Horizon redshift determines where the power law cuts off. We also model the mean host DM contribution and an FRB bias factor that controls the amplitude of the second power spectrum here. We have one parameter, Loc, to model the instrument localization error. So we assume within a scale defined by Loc, CHIME can't localize FRBs well enough, and this causes suppression of the cross-correlation signal, which we can model as a Gaussian beam suppression factor. And finally, we have one parameter, K-cut, that models feedback physics. Recall that feedback pushes baryons outside of galactic halos and decreasing the correlation strength between electron and galaxy. So we can model this as an exponential decay on the electron-galaxy cross-power spectrum, with the parameter K-cut defines a characteristic feedback scale. So within the scale, the presence of baryon is reduced. So we use MCMC to sample these parameters given our measurement. So on this plot here, the blue data points are once again the power spectrum measurement I have shown you already. The black curves, they are randomly drawn from the posterior distribution to show you the allowed amplitude and shapes that can fit the data. And out of the posterior, the maximum likelihood signal model has a delta chi-square of 31, equivalent to a detection significance of 5.1 sigma. So this is the first time this signal is measured in Fourier space as power spectrum, and it's also the first definitive detection of correlations in DM with cosmic structure. So all the inferred parameter values, they are within their expected range. And in particular, I want to highlight the parameter K-cut that models the feedback physics, and it is well constrained to be around 1 megaparsec. So what does this tell us physically? So on the face value, this parameter being 1 megaparsec means electron distributions are smoothed out to megaparsec scale. So the correlation between electrons and galaxies decrease within the scale. It further suggests that feedback has driven baryons out of group scale halos. So galaxy groups become deficient in baryons. To demonstrate this with simulations, on this plot, I'm showing you the galaxy, the electron galaxy power spectrum in Illustris TNG using this dashed curve here. And the same quantity from our K-cut measurement is also plotted in the solid curve with 1 and 2 sigma error bands. So we can see that our measurement matches Illustris TNG quite well at large scale. But then our measurement starts to dip around 1 megaparsec. And the tension grows. It really grows once we reach hundreds of kiloparsec, so close to virial radius of galaxies. So our measurement really suggests suppressed baryon presence within galactic halos, and therefore suggests stronger feedback than what's used in Illustris TNG. However, keep in mind that this is a one-parameter fit, and the exponential decay, that functional form, is rather ad hoc. So in the future, we need more careful modeling to place precise constraints on feedback physics. And last, I want to put the conclusion of our study in context of others. So first, from Marion's talk yesterday, we saw that a stacking analysis also found excess electron out to megaparsec scale. So in some sense, the correlation function here is a real space analogy to the power spectrum we measure in Fourier space. So it is good to see that we have reached similar conclusions. And outside of FRB world, X-ray stacking analysis, as well as CMB foreground studies, have also found evidence for stronger feedback than those in simulations. So for example, I'm showing you the KSC measurement from DESI 01 result in the brown data points here. And all the colored curves, they are the predicted values from simulations. So basically, at the scale around 1 megaparsec and below, we can see that the simulations overpredict the amount of baryons within the galaxy halos. This once again shows that the simulations don't seem to have strong feedback. So their feedback are weak and cannot push enough baryons outside of galaxies to match the data. And finally, I want to look back to using FRB to study the IgM. So other techniques like X-ray and SZ, they are sensitive to IgM gas properties like density, temperature, and velocities. But FRB DM counts all the electrons along the line of sight, therefore is a model-independent way to study the IgM. And in the near future, the power of FRB cross-correlations will only grow with the upcoming experiments like CHORD and DSA 2000, which will give us around 10,000 FRBs per year. And many of those will come with Redshift as well. So this is going to make FRB a prominent tool to study IgM and feedback. And finally, I just want to leave my conclusion slide here and take questions.
Thanks so much. So what questions do we have?
Let's see, stand up. I am yours for.
Is someone speaking right now?
Hi, Ilya Khrykin here, Católica University Valparaiso, Chile. So one of your conclusions was that TNG doesn't have strong enough feedback based on that plot with K-cut. What happens if you compare this to Simba, for example, which apparently has stronger feedback than TNG? How does it change that comparison plot?
Yeah, that's a very good question. So right now, so on this plot, we only compare that with Illustris TNG. This is more a way for us to show that, yeah, we can make this measurement and we can compare this to simulation. But again, the caveat is that this is only one parameter fit. So definitely we want to have more careful modeling before we start to compare with other simulations. So you are completely correct. That will be indeed the next step to do. But for now, we don't make that comparison yet. But that can be quite straightforwardly done in the near future.
Cool, thanks.
Liam, go ahead.
Haochen, that was a very clear and exciting talk. Congratulations. My question is, if you have a halo model and you have a measurement of PEG, can you estimate things like FIGM? There's not a one-to-one mapping between FIGM and power spectra, but there are a range of allowed FIGMs, if you see what I mean.
Right, right. Again, I think that ties back to how we model things. I think one straightforward way could just be we compare our power spectrum with simulations. So basically, in simulations, use FIGM as input parameter and tune that parameter to see the resulting power spectrum as output from the simulations, and compare our measurement with the simulated values. So yes, I think If there's no direct theory that's linking the PEG with IGM, then we have to use simulations to compare our measurement with the simulated results. I think that would be the way to go.
Okay, thanks so much. That's all the questions we have time for. Let's go to Zoom for the other ones and thank the speaker again. Okay, so next up is Calvin Leung on stellar mass, dispersion measures, and baryonic feedback in galaxies. Calvin, I will hold up a little sign that 1 minute.
Give me a minute. Thank you. Oh, no. Oh, no. Oh, it's okay. This is fine. Okay. Wow, Haochen, that's a hard act to follow, and I'm really excited about that result. Haochen's result told us about baryonic feedback around large mass halos. We heard from him and Maryam's talk that they're probing electron distributions on 1 megaparsec scales. That's sort of the size of a typical galaxy cluster. I'm going to approach things from the other end, where we look at individual FRB host galaxies and see how trends in the dispersion measure of the host galaxy vary as a function of stellar mass, coming to a rather unintuitive conclusion, which we can explain through baryonic feedback. My name is Calvin Leung. I'm a Miller Fellow at UC Berkeley, and in addition to VLBI, I'm very excited about all the baryonic feedback studies we can do using FRBs. As Haochen and others have mentioned, if you look at the distribution of light in Illustris and Illustris TNG, things look really similar. However, if you look at their gas distributions, things look quite different. And this is why you need gas probes in order to really study feedback. We've been doing these galaxy simulations for decades, which have been making these predictions because the CGM and the galaxy and the environment, even on larger scales, all talk to each other through processes like gas cooling, star formation, stellar feedback, and AGN feedback. However, until now, it's been really hard to probe some of the like the outskirts of galaxies. And FRBs gives us a great way to do this, a temperature and metallicity insensitive probe of the circumgalactic medium, as Leung said yesterday to kick off this probe session. FRBs are nice. Here are some FRBs that we've detected in our latest catalog, the first catalog of outrigger localized FRBs. For this work, we used the catalog, the outrigger station that we commissioned near CHIME on a 66-kilometer baseline. This is an excellent telescope for finding local universe FRBs because it's a bit smaller than CHIME and because VLBI calibration turns out to be a lot easier on a 66-kilometer rather than a 3K kilometer baseline. Here are some beautiful FRBs. These are actually some of the first local universe FRB catalog coming out of CHIME. And I'm very happy to say that as a result of our collaboration with F4, we have host galaxies and redshifts for a large fraction of these galaxies. Most of these sources are at redshifts less than 0.2. And at redshifts less than 0.2, it turns out that the largest contributor to the DM is not the IGM, as Liam was talking about yesterday, but instead the host galaxy. So you can just start to curate a large sample of local universe FRBs, as Liam was talking about, and start to see what you can say about the circumgalactic medium. Here's 20 FRBs. This is everything we have in the literature, selected according to a set of quite stringent criteria. We look for FRBs in the local universe. We only select based on host galaxies, or else the ISM will contribute. We're going to choose bursts which are not scattered so that the local circumburst medium does not contribute to the DM. We're also going to choose hosts which don't appear in group and cluster catalogs. So we know that we're looking at the DM host really from isolated star-forming galaxies. We select on stellar masses within a certain range. We use catalog stellar masses where possible. These are all done using Prospector or similar SED fitting codes. For two systems, we can't do that. And we also standardize the IMFs using all those fits to a Shabir IMF. So if you report what IMF you used in your paper, I saw it. And if you didn't report what IMF you used in your paper, I also saw that. Finally, we also choose sources at high galactic latitudes. So with these 6 or 7 very stringent criteria, we now have a nice sample of local universe FRBs. which we can use to measure what I argue is probably coming from the circumgalactic medium. This takes a sample of roughly 100 FRBs in with known spectroscopic redshifts to something like 20, which are shown on the right. Because these sources are so local, you don't have to worry about interlopers along the line of sight. We're going to treat them statistically and ignore foreground contributions. And then we're going to compare what we get for DM host to the total DM. So here's the 3 contributions to the total DM. And we're going to subtract off the galactic and the cosmic contributions to that quantity, just comparing what we get for DM host. As we heard from Isabel yesterday, these theory predictions differ as a function of feedback model. And what we see is that they vary in terms of how strong feedback is, how much gas they push out. And we can actually start to see this in DM host. So if we plot the DM host as a function of stellar mass, we actually start to see with this curated sample, not a positive correlation, but a negative correlation. So in other words, as you make your galaxies bigger, they don't necessarily have more gas in their environments. The fit to the data is shown in gray. The data are shown in green and blue, binned into 2 subsamples, redshift less than 0.1 and a high redshift bin of 0.1 less than 0.2. In contrast, the models all predict no correlation or a positive correlation with the DM. Since I'm out of time, I'll take any questions later. Thank you.
Thanks so much, Calvin. So we're going to switch session chairs now. Andrea, if you could come up, and then also Kendra, come and start getting ready.